Hello everyone, thanks to be here. I am Joseph Gallego, and today I'm going to present to you fast kernel density estimation using density matrices and Fourier efficient. I collaborate with Juan Osorio and Fabio Gonzalez, and we come from the National University of Colombia in Bogota City. So let me introduce our method with a little of the background. So there are three parts in my PhD thesis that we want to combine. The first part is the machine learning approach. The other part is the statistics. And with all of this, we want to develop anomaly detection methods. Right now, we developed several ones of in the ideas that I'm going to present to you, that I am presenting in another conference. The statistics, there are a really big algorithm that calls kernel density estimation, that maybe one of you have been used in research, maybe not. And there are other connections that will be density estimation. What is density estimation? The idea of density estimation is that there are a random variable that we want to estimate given a data structure, given data points. We want to approximate this unknown probability density function. And there are really two main approaches to be able to obtain that density estimation. That is a parametric or a non-parametric density estimation. There are several applications that you can solve using density estimation. There are generative models, density estimation, anomaly detection, and classification. Among others, you can really solve a lot of different kinds of problems. So, because of that, I want to introduce kernel density estimation. That is one of the base algorithms that we use in our method. Kernel density estimation is a non-parametric density estimation method. So we don't assume any particular assumption about the underlying probability density function, and we can calculate the density only using the like you see there in this equation. I only use the training data points. Yeah, and you can prove that kernel density estimation is an unbiased estimator of the probability density function. One of the most used kernel is the Gaussian kernel, that is this one. Maybe one of you have been used this kernel. And the idea is that we use the data points, and maybe if you don't know this method, it's like putting Gaussians in every data points. And at the end, you take the mean value of those data points, and using that, you can estimate the density function. What is the problem with kernel density estimation? And is the thing that we want to solve is that this is an inefficient memory-based algorithm because you need to store every data point in the training stage. So we need to use every data point. When you have high-dimensional data, it has really struggles. So maybe when you have more than 1 million data points, the algorithm is worse, but it takes so much time, so it's really difficult to use. Also, in this time where deep learning is the paramount importance in every algorithm right now, the problem is that kernel density estimation is a non-differentiable algorithm. Therefore, we have the training phase is a big O in the process time, is a big O n in the memory footprint, but in the testing phase, you will have O big O n of the process time. So the problem here is that if you have many training data points, these algorithms will not work. So our problem statement and what we want to solve is we want to develop a new method that is a memory-based algorithm, is simple, it is interpretable also, the training difficulty is not so high, it can be differentiable, so we can combine with other deep learning approaches, and maybe that is good for anomaly detection. Why good for anomaly detection is also, as the other presenter for my PhD. So, with all of this, I want to introduce you to new topics. Okay, I know that I am introducing a lot of them, but random Fourier feature and kernel methods are really interesting ones and are using a lot right now in deep learning approaches. Kernel methods have been known for several years right now, maybe 30 years ago, and with course of BACMIC and other ones, where we want to introduce a future space using a Kernel function, yeah? And the idea is that we can evenly produce infinite dimensional or high dimensional space using the Kernel function. But the problem, if you ever use the kernel methods, you know that it has a really big footprint, and maybe you need to calculate the ground matrix, it will take like big O n squared. So the complexity is really high. So what is the idea? Okay, IBERAMIA in 2007 proposed one Fourier feature where you can calculate explicitly the kernel method using only the dot product. So using this notation and using this technique, you can use only the dot product to calculate the kernel and avoiding the general cost of kernel methods. So the result is that we can learn models involving nonlinear kernel using only linear models. We improve a little bit the random Fourier features, and we propose adaptive Fourier features to improve kernel density estimation. I am going to explain how can we use this method in reality, but I need to clarify this. The other formalism that we use is density matrices. Density matrices is used in quantum machine learning, where we want to, it's not quantum machine learning, sorry, it's from quantum physics, and it's a formalism that you have a state of, given a state of a physics system, you can calculate the probability that a given system has in certain state using only the probability. And the probability is using the Born rule, so you can calculate the probability of a given state. But the problem is, so density estimation, density matrices, can we use density matrices for statistics and machine learning? We prove in another journal paper that this is possible, and the idea is that there is a more general model of probability. As you know, in quantum mechanics, we can combine the classic probability and the quantum probability, and it has a lot of advantages of using this kind of models and this algorithm. So you can, and the real good thing about density matrices is that you can combine linear algebra and probability. So you can calculate probabilities using only linear algebra. So it's really interesting one. And at the end, I will not explain this part, I will only explain briefly. And the thing is that we can show, and I am going to show you that the density estimation that I am presenting here, we can calculate it using a random Fourier feature and the kernel density estimation. This is what I am going to talk next. So the problem here is that using density matrices, we can calculate categorical distribution. It's obvious, but the problem is that it's inefficient and it's not very useful. So the thing is how we can use density matrices and random Fourier features to calculate arbitrary distributions that in this case is not obvious because we include a mixture, a bunch of probability distribution functions. So for that reason we propose density matrix kernel density estimation that is an efficient approximation version of kernel density estimation. It's a non-memory based algorithm. Also is differentiable, so we can combine with other development approaches. We can train the model in two ways. One is an optimization tree, one is using a sum. We are really calculating the density matrices is a sum, but we also can further tuning the density estimation using the stochastic variability descent. So the method is like you can see here. You take all the training data points to produce a random Fourier feature. So at the end, the sum will be only the sum of random Fourier feature representation of each point. And so I will explain how we can derive this method. It's not as hard as you think, but is what I am talking about right now. So kernel density estimation and density matrices kernel density estimation. One of the first idea that we can have right now is that if you have random Fourier feature, you can have a linear strategy that is the one that I am explaining here. You have the sum of all kernels of each training data points, and after that, because you can have the random Fourier feature representation of each point, you can join the summation inside the equation. So at the end, this part that is the kernel of both points, you can join the sum inside the dot product. And at the end, this is a linear strategy. You can calculate in this way the density estimation, and you can use this raw train that is a matrices that capture the density of the training data points because of this relationship that you can see here. But we can further, okay, so right here, the training is O, B, O, N, D, where B is the dimension of the random Fourier feature, because for random Fourier feature, you need explicit dimensions. And the thing is that at the end, the prediction time, when you have a new data point, is only BOD. So it's only related with the dimension of the embedded data space of the random Fourier feature. So with this new algorithm, you can calculate kernel density estimation without using everyday training data points and without store everyday training data points. But we further improve this algorithm, and we can for sure take the square of the kernel. We can show that it is a Mercer kernel, so it doesn't have any problem related with the positiveness of the kernel, and using a similar approach that we take with the linear strategy, we can see that we can join also the summation inside the equation, and here is only related with the training data points. So, similar as kernel density estimation, you can combine and you can have a raw train that you can see here. The interesting part here is that this one that you can see here, is a density matrix. So, if you have algorithms that runs maybe in a quantum computing, you can use this kind of strategy. We are right now with other colleagues in our lab producing different kinds of algorithms using this strategy, but with quantum hardware in quantum computer hardware. So, and at the end, we can calculate the density probability for each new data point. Okay, so as you can see, this is the algorithm. It's not as difficult as I mentioned. And at the end, you can calculate the density matrices. The idea here is that this is like calculating the Bohr rule. This is similar to quantum computing. As I mentioned before, we can also further tune the density matrices. So we can use spectral decomposition of the density matrices, as you can see here. And the idea with this is that we avoid the dimensions of the random Fourier feature. So we can, if for instance the dimension of the random Fourier feature is 1000, we can further we can not use the 1000 dimensions, but only maybe 100. So it is we just use the stochastic gradient descent, and we can further turn the parameters of both these matrices. And at the end, the prediction time is not related with the D, that is the dimension of the random Fourier feature, but it's only related with the R, that is the spectral decomposition run of the matrices. With proof that it has is bounded to the right, as you can see in the paper. You can see all the derivations, and it's a lower bound of the kernel density estimation. Sorry, I don't mention that. And at the end, this is the algorithm that we propose. So every data points pass through each part of this network. Is firstly, the first part is the random Fourier feature. After that, for making a right quantum density estimation, we use a normalization state, and at the end we have the quantum measurement. The loss right here is training using the log likelihood. And what we can do with this? Okay, there are several things that we can do. Here during our lab, we are proposing new methods in classification, new methods in regulation, new methods in unsupervised learning, also in clustering. But my idea here is to show density estimation. As you can see, this one is the training data set. You see that it's a really difficult one. It's not an easy task for an algorithm to capture the training and the density of the set. And as you can see here, this is the kernel density estimation, and this is our method. That is density matrices, kernel density estimation. Our method has a lot of advantages compared to KDE, and as you can see, we only are restricted with the number of testing data points. And we don't care about what are the number of the training data points. So as you can see here, this is KDE, kernel density estimation. And the problem with kernel density estimation is that when the dimensions blow up, the problem is that you have maybe few data points, few training data points, the density estimation will be not as good as you expect. And for this, maybe you can see here that the density matrices Kernel density estimation, when you use the same amount of training data points, you get like the same. Maybe our method is maybe lower in this part, but the thing that we can use much of the training data points. You can see here that we are using like 10 million data points. That using this kind of huge data set in kernel density estimation is not really possible. We also prove with these 6 data sets from the state of the art. And there are really difficult ones, like this one. There are functions that we want to capture the density estimation. And we show that our model, when the training data set is really small, we are not as good as the state of the art. But when the training data set is bigger than 10,000 data points, we are better than state-of-the-art methods. Also, we show that, we also, this is in different kinds of functions. And we also show that our method is better in mean average error and also in CPU time, as you can see here. There are other, we are also proposing this for neural density estimation. This is another article that is approaching with similar algorithm, and we show that our algorithm is better than a state-of-the-art neural density estimation method like round tree that is neural flows. So, finally, I will mention the conclusions. So, density matrices kernel density estimation use the kernel approximation driven by random feature and density estimation. It's not a memory-based algorithms, as I mentioned. This can be combined with deep learning methods, and it shows better time performance than state-of-the-art algorithms over 16 density estimation datasets. So, thank you. Oh, okay. Right here, what I showed you is only in normal computers. It's not in quantum, but we are testing right now this same algorithm in quantum computers.
And in that case, this complexity analysis
no, it's related because at the end we can send all the training data points. Yeah, there are maybe some parts that are not the same. And the performance, right now, the difficulties with quantum computers is that we can only use a little qubits. So the problem is, for instance, is that for using this, for producing this estimation, we need like the amount of Fourier features need like 1,000 dimensions. But in the case of quantum computers, you can do it right now with this big estimation. You can only use like 6 or 12 of 12 qubits. But yeah, we are showing right now that we can use in quantum computing, but maybe the reality is that right now the hardware are not in the state that we need to provide this kind of hardware.
Any other question? Second, I'm sorry, but I'm not familiar with the random Fourier feature, so what you do is just I saw a design.
Yeah. Random Fourier feature is a really good algorithm that is this. The idea here is that we use a theorem that calls Wagner theorem. The thing is that we can provide this expectation. And the thing is that we sample from a normal data, from a normal distribution, and also for a uniform distribution. And at the end, we can calculate this as a cosine of the A of x times the W's that are the number that you sample from the normal data points, normal distribution, and summing and uniform. And at the end, the Rahimi shows that if you use these algorithms, you can approximate the kernel using only the sample that you sample from the normal.
You see that also to calculate explicitly the value of the point in that space.
Yeah, it's really interesting. Yeah, because in reality, you know that, for instance, the Gaussian kernel is an infinite one, but it is you have like a, for me, or my idea that I have is that it's like the summations of the points. It is like the Taylor series that after some points it doesn't care about.
That's pretty interesting. Thank you. Any other question? No? Let's thank Joseph again.